There is a fact about your physical reality so profoundly counterintuitive that even after you fully understand its mathematical machinery, it continues to feel like an impossibility. You are not moving through time at the same rate as anyone else on this planet, not your neighbor, not a scientist orbiting the Earth aboard a space station, not the atoms vibrating inside a clock resting on a mountaintop compared to an identical clock sitting at sea level. Every single object in this universe is aging at its own personal rate, governed not by some arbitrary biological quirk, but by the precise geometric structure of the universe itself. We carry a deeply embedded assumption about time. It feels like a background condition of existence, a steady, invisible river flowing at one single uniform speed through which all things move together. You feel yourself carried forward. You assume everyone and everything else is carried forward at that same rhythm. The sun rises, the seconds accumulate, the years pass, and in your lived experience, time feels like the most democratic and universal feature of reality. It gives no special treatment to anyone. It ticks at one pace and one pace alone. That assumption is mathematically, physically, and demonstrably wrong. The revolution that dismantled this ancient intuition did not come from philosophy or speculation. It came from the geometry of spacetime itself, laid bare through the equations of Albert Einstein and confirmed through experiments so precise they have left no room for doubt. What those equations revealed is that time is not a universal background. Time is a physical substance woven together with the three dimensions of space into a single four-dimensional geometric fabric, and that fabric bends, stretches, and curves in direct response to the presence of mass and energy. Where the fabric curves, the dimension of time itself slows down. This is not a metaphor. It is a measurable, quantifiable, physical reality. To feel the weight of this, consider that river analogy with fresh eyes. Imagine you are floating quietly in an enormous, smoothly flowing river. From your perspective inside the water, the entire river feels as though it moves at one single uniform mathematical speed. The current carries you forward with no variation, no acceleration, no deviation. You assume the entire body of water obeys this same uniform law. But then you look deeper, down toward the riverbed, and you notice something remarkable. Near the heavy boulders resting at the bottom, the physical water visibly, unmistakably slows. It catches itself in deep, curling geometric currents, twisting and pooling against the stone. The mass of those boulders alters the behavior of the water flowing around them. The universe operates in this precise manner, with time playing the role of that river and massive physical objects playing the role of those boulders. The planet beneath your feet right now, the sun at the center of this solar system, the supermassive black holes anchoring the centers of galaxies, every single massive object physically warps the geometric fabric of space-time around it. And where that fabric warps, the passage of time itself changes. Time flows at a measurably different rate inside a gravitational well than it does in the open emptiness of deep space. This phenomenon carries a precise scientific name: gravitational time dilation, and it is not theoretical speculation. It has been measured, verified, and is so physically real that the Global Positioning System satellites orbiting the Earth must account for it in their calculations. Those satellites sit higher above Earth, experiencing a weaker gravitational field than clocks on the ground. Because of this, their atomic clocks tick faster than identical clocks at sea level. The difference amounts to approximately 45 microseconds per day. If engineers did not correct for this discrepancy, GPS positioning would drift by several kilometers every single day. The technology that tells you where you are on this planet works precisely because engineers take gravitational time dilation seriously as a physical fact. To understand why mass curves time, you need to follow the physics back to its source. Einstein's general theory of relativity rests on a foundational insight he called the equivalence principle. Imagine you are inside a sealed room with no windows. You feel a downward force pressing your feet against the floor. You have two possible explanations. Either you are sitting still on the surface of a planet whose gravity pulls you downward, or you are in deep empty space inside a rocket accelerating upward at precisely 9.8 meters per second squared. From inside that sealed room, using only the sensations available to you, you cannot distinguish between those two situations. They are physically, mathematically, perfectly equivalent. Gravity and acceleration are not merely similar in their effects. They are geometrically the same phenomenon described from different frames of reference. This equivalence led Einstein to a stunning geometrical conclusion. If gravity and acceleration are equivalent, and if we already know from special relativity that motion through space affects the passage of time, then gravity must also affect the passage of time. The logic is airtight. The mathematics confirmed it, and the universe obediently agreed. The deeper you sit inside a gravitational well, the more that massive object stretches the geometry of space-time around you, and the slower your personal experience of the temporal dimension becomes. Your biological clock, the chemical reactions firing inside your neurons, the oscillations of the atoms in your cells, the vibrational frequency of every particle composing your body, all of it ticks at a rate governed by the local curvature of space-time at your precise location. There is no universal background clock ticking above all of this, setting the rhythm for everyone. Each location in the universe possesses its own local rate of temporal flow, determined by the geometry of space-time at that specific point. Now carry this insight to its most extreme physical manifestation. Consider a stellar mass black hole, an object so gravitationally dense that it represents the most extreme space-time curvature in the known universe. An observer watching from a safe distance would witness something that initially appears to be a paradox. If a spacecraft were to slowly descend toward the black hole and hover at a fixed distance from the event horizon, the clocks aboard that spacecraft would tick measurably slower than the clocks of the distant observer. If the spacecraft descended even closer, approaching the edge where space-time curvature reaches its maximum measurable limit, the temporal discrepancy would grow catastrophic. For the distant observer, watching through instruments, time aboard that spacecraft would appear to nearly freeze. A second aboard that craft might correspond to years or centuries passing for the distant observer floating in the gentler curvature of open space. From the perspective of the crew aboard that spacecraft, nothing feels unusual. Their clocks tick normally, their hearts beat normally, their thoughts unfold at what feels like a perfectly ordinary pace. They have no direct sensation of the gravitational time dilation warping their experience of time. They simply inhabit a region of space-time where the geometry of the temporal dimension has been stretched so severely that 1 second of their local time contains an enormously larger slice of what a distant observer would call cosmic time. They are living in a different temporal neighborhood of the same universe. This is the precise point where the ancient concept of a shared universal present dissolves. Philosophers and physicists once took it as self-evident that there exists a single moment called now, a cosmic stage on which all events across the universe occur simultaneously. Einstein's physics demolished this assumption with a different mechanism, one that arises not from gravity alone, but from relative motion. Special relativity demonstrated decades before general relativity that two observers moving at different velocities through space will mathematically disagree about which events are simultaneous. Simultaneity is not a fixed physical feature of reality. It depends on your state of motion. If you and another observer are moving at different velocities, and you each draw a line through space-time representing your personal slice of now, those lines tilt relative to each other. Events that occur at the same moment for you occur at different moments for the moving observer. The disagreement is not a measurement error or a limitation of perception. It is a geometric feature of space-time itself, rooted in the Lorentz factor, the mathematical expression that quantifies how space and time transform between frames moving at different velocities. The Lorentz factor grows as relative velocity increases. At everyday speeds, the effect is immeasurably small, but as velocity approaches the speed of light, the factor becomes enormous. A clock aboard a spacecraft moving at 99% of the speed of light would tick at a fraction of the rate of a stationary clock. The crew aboard that craft would age far more slowly than anyone remaining behind. This is not science fiction. Particle accelerators routinely verify this phenomenon. Unstable subatomic particles that would normally decay in a tiny fraction of a second survive far longer when moving at velocities close to the speed of light, their internal clocks dilated by their motion precisely as relativity predicts. Combine the time dilation produced by velocity from special relativity with the time dilation produced by gravity from general relativity, and you arrive at a universe where no 2 points in space share the same rate of temporal flow. Every object follows what physicists call a world line, a path traced through the four-dimensional geometry of spacetime. Along that world line, the personal time of that object, called its proper time, accumulates at a rate determined by the curvature and motion the object encounters. Two objects beginning at the same spacetime location and arriving at the same spacetime location by different routes will have accumulated different amounts of proper time along the way. Their ages will differ. Their biological clocks will have counted different numbers of heartbeats. This is the twin paradox, and it is not a paradox at all. It is the straightforward consequence of geometry. All of this leads to what may be the most philosophically striking implication of relativistic physics, the block universe. If simultaneity is relative, if different observers moving through spacetime draw different slices through the four-dimensional geometry when defining their personal now, then there is no privileged moment called the present. There is no universal knife cutting through spacetime to separate the past from the future. Instead, physicists are led to a picture of reality in which all moments of time, past, present, and future, exist simultaneously as fixed structures within a four-dimensional geometric landscape. The terminology physicists use for this picture is the block universe, though its more formal name is the eternalist view of time. In this geometric model, the universe does not unfold or evolve, it simply is. Every event that has ever occurred or will ever occur already occupies a fixed location within the four-dimensional block. The birth of the solar system, your current moment of reading these words, the distant future cooling of the universe into maximum entropy, all of these events are permanent geometric features of the same static four-dimensional structure. What we experience as the flow of time, the sensation of moving forward from one moment to the next, is not a feature of the external physical universe. It is a feature of consciousness moving along its world line through a static geometric block, sampling different cross-sections of that structure and experiencing the sequence as movement. This is profoundly disorienting precisely because the sensation of temporal flow is so immediate and compelling. The feeling of the present moment arriving and the past receding feels more real than almost anything else in conscious experience. Yet the mathematics of relativity offers no mechanism for a universal moving now. The equations describe world lines and proper times and space-time intervals. They contain no variable corresponding to a global flowing present. The feeling of now is real as a biological and psychological phenomenon. But the physics suggests it may be something the nervous system constructs from its local experience of spacetime, rather than something the universe itself possesses as an objective feature. There is one further layer worth exposing. The second law of thermodynamics introduces the concept of entropy, the tendency of physical systems to evolve from ordered states toward disordered ones. Many physicists believe the psychological arrow of time, the reason we remember the past but not the future, the reason we feel time moving forward rather than backward, is rooted in this thermodynamic asymmetry rather than in any fundamental feature of the spacetime metric. The laws of physics at the fundamental level are largely time-symmetric. The equations of general relativity, quantum mechanics, and electromagnetism work equally well whether time runs forward or backward. It is the thermodynamic gradient of entropy, the fact that the early universe was in an extraordinarily low entropy state, that provides the physical arrow distinguishing past from future. So when you feel time passing, when you experience the weight of years accumulating, when you sense the irreversible one-way movement from past toward future, you are experiencing simultaneously the geometry of your personal world line through a curved four-dimensional space-time, the thermodynamic asymmetry imposed by the initial conditions of the cosmos, and the local biological computation of a nervous system that constructs the sensation of temporal flow from the physical signals available to it. None of these mechanisms require a universal background clock. None of them require a shared cosmic now. All of them emerge from the mathematics of a universe in which space and time are unified into a single, flexible geometric structure shaped by mass, warped by energy, and measured differently by every single observer, moving along their own unique path through its four-dimensional geometry. The universe does not tick, it curves, and in that curvature, time itself becomes as flexible as space, as physical as matter, and as profoundly personal as the body through which you experience it.